Thanks for joining us for the first video on the series on alkynes. And the main thing here, except for the first reaction we're going to talk about, a lot of the reactions are going to be total parallel to the alkene reaction. So please don't think of them as a separate things. Just sort of extend and apply what we've already learned about alkenes to these, and they should be pretty easy. Okay. The first thing we're going to learn about alkynes is a little bit unique to alkynes, which, by the way, we're not going to do nomenclature stuff for this functional group, but I just want you to know that the ending is going to be "-ine" for alkynes. The first thing that's unique about alkynes is the terminal alkyne proton is kind of acidic. For instance, if you look at the pKa of this, it's around 25. Now, maybe that's not super surprising, but if you compare the pKa for alkane, regular sp3 proton, right, this is around 50. Alkene is a little bit lower, 45, and alkyne is 25. That's order of 25 magnitudes different, which is like, bigger than it's kind of in the same order as Avogadro's number. So it's a humongously different acidity compared to regular alkanes, which if it loses a proton, right, this negative charge would result for alkene. It would be this, alkyne, it would be this. And the reason why there's such huge difference in acidity is because of the orbital. Remember that we talked about, when we first talked about carry rule, right? The atom's electronegativity, the orbital matters. Notice that this lone pair of electrons, they're in an sp orbital, these in sp2, this is in sp3. Remember, the more s character you have, sort of the more electronegative it is in a way, and so for that reason, this is the most stable. This carbon is a little bit more electronegative in character, so that explains that. And this is called an alkynide ion, not surprisingly, because it's an anion made from an alkyne, right? And the the reason why that is synthetically also useful is because if you apply a strong base, like say, so this is called sodamide, NH2 minus, or alkylithium, or Grignard, right, or even maybe I'll add LDA. If you don't know what that looks like, you should go look it up. The structure up, those would all work, okay? And remember, Grignard is not just a nucleophile, but it's also a very strong base. And in this structure, there's nothing that nucleophile could add to. There's no electrophilic anything, and so for that reason, the only thing that happens with Grignard would be that the terminal proton gets deprotonated. Now notice that this only happens with a terminal alkyne, meaning the alkynes on the end of the chain, for the obvious reason that if it's inside the chain, there's no proton on it, right? Now remember from chapter 6, I think, this is an excellent nucleophile. Alkynide ion is an excellent nucleophile. It's kind of skinny, narrow, and it's nucleophilic, and so this is gonna add to the this can add to carbonyl. So just to maybe show you the mechanism, right? Grignard can take the proton off, right? Forms the alkynide anion. That's the end of that first step. Now this great nucleophile could add to carbonyl, and remember that is an excellent way to make an alcohol. After it gets protonated in the aqueous workup step. Right, that would be the product, and the product, of course, would be like that. Okay, I'll let you think about the products that result from these, and then we'll compare answers in class, but please work on these on your own. Another type of reaction we'll learn about alkynes would be reduction, and this is basically the same thing we've seen already in alkene chemistry. Okay, so what happens here? Well, it's the same kind of thing we saw before for hydrogenation, right? Hydrogenation just means you add two hydrogen atoms across a pi bond with a palladium, and so that's not too surprising here, hopefully, right? That this would be the result. Two molecules of hydrogen add here instead of just one, right? So that's really all I would say about that. I want you to think about the products to this. We'll compare answers during class. Now, the only sort of new type of hydrogenation we might discuss is the partial hydrogenation. And the only difference is we use quinoline, which is a molecule that looks like benzene and pyridine fused together. Looks like that. And then palladium deposited on barium sulfate, or sometimes calcium carbonate is another option that you might see. That is called a poisoned palladium catalyst together with barium sulfate and quinoline or calcium carbonate. It just, like these things, reduces the efficiency of the palladium metal. And so for that reason, what you get is only once hydrogenated product. Okay. Now notice that the stereochemistry here is cis. Okay, and hydrogenation, we don't want to talk about the exact mechanism per se, right? But maybe we'll just think about the fact that these two hydrogens add, here's palladium, from the same side. Simultaneously. It's a syn addition, right? And that explains the cis formation here, right? I should also add barium carbonate. I just remembered that's another possibility, but because poisoned palladium is not as reactive, the reaction just stops here. It doesn't go further to the alkane all the way. Okay, so that's really all there is to partial hydrogenation. Now, there's another type of reduction reaction that is kind of special to alkynes, and this would work even with terminal alkynes, even though I'm showing internal alkynes. And this is kind of very different than what we just talked about, because you actually get trans double bond, okay, as a product. And this requires sodium metal, that's not sodium cation, but sodium metal with zero charge. And we're going to use ammonia as a solvent. And this is actually the same setup that is often needed to make meth. So you might get flagged if you try to acquire these reagents, sodium and ammonia liquid. But I have to warn you, the mechanism is going to be a little bit different, and since you're going to have to kind of learn about a more radical mechanism very soon. This might be a good introduction. Now, sodium, remember from Gen Chem, it has just one valence electron, right? So that it wants to get rid of to have octet, because once it gets rid of that, the second shell is going to be filled, right? Na plus is a filled octet atom or ion, so it wants to get rid of it, and it does. Now, when we display the movement of one electron, I want you to notice how this is a half-headed arrow to indicate it's a movement of one electron. Now, if that gets deposited at this carbon, which remember, sp carbons are somewhat electrophilic or electronegative, and that's why this happens. This carbon is going to have too many electrons, so these need to move over as a pair, right? So then what happens is you get this radical anion intermediate. And the thing about this is these electrons will want to be as far apart as possible. Remember the Vesper theory principles. Maybe we'll say hashtag Vesper. Okay, and that's why they're going to be in the trans geometry instead of, like, say, cis, right? And then what happens is this anion could pick up a proton. And now it's just sort of a radical. Now, remember, well, I guess I didn't say it, but so you typically use an excess amount of sodium here, and so another atom could deposit another single electron, right? And that will give us anion on this sp2 carbon that can once again grab proton from the ammonia. Now, given this mechanism, you might think the reason for the choice of ammonia as the solvent is because, you know, it's a protic solvent that could donate a proton at these two steps, but that's actually not quite the reason why. Ammonia is able to solubilize sodium metal, and encourages it to give up its electron, and this electron technically just sort of first dissolves into the ammonia liquid, and then that's what gets added instead of directly sodium passing it on to the alkyne. So you get this solution of electron, which is kind of an amazing thought, and it's this beautiful dark blue solution that's really pretty if you ever get to see it. But anyway, you could also do this reaction with other alkali metals like lithium. Okay, so I want you to do this problem before a class, but we'll compare notes then.